Hi, everybody, and well, kudos to Diana and the Understand Energy team. Most places that have an intro energy 101 type course, they cover all the resources, fossil, nuclear, renewables, hydro, et cetera, and thereby leave out half of the energy system, namely the demand side, and one of the most important and cost-effective resources, namely the energy efficiency resource. So I will talk about that and help fill that gap. I'll go through a little bit of the kind of nerdy information that we have to collect in order to describe the energy efficiency resource. I'll talk about some of the barriers or challenges to implementing it and thus justifying why we need policies and programs and incentives and new business models to capture the efficiency resource. And I'll take out a couple of examples, codes and standards and utility procurement programs to illustrate that, and then sum up with describing how efficiency fits into an overall strategy of energy decarbonization. So there's a long history of this, and I go back that far actually to the 70s when the idea of energy as a topic arose in the public consciousness. And the question at the time and the challenge was, is there enough of the resource? Are we going to run out of oil, for example? And we were queuing up in gas lines, and Elvis talked with the president. That was important. Around that time, though, a few people started asking a different question, and it was really spearheaded by our colleague Amory Lovins, with whom I teach a course here in the winter and spring. He too got to meet the president, and he, along with a few other colleagues, such as the great physicist Art Rosenfeld, our friendly environmental lawyer Ralph Cavanagh, and Governor Brown, in his first excursion when he still had hair as governor, started pursuing the idea of energy efficiency as an alternative to ever-growing energy demand. And in a really landmark paper in 1976, Amory posed really two fundamental questions that changed the whole paradigm of the energy field. And the first was, the mainstream projection of energy use, now this is going back to the 70s, so that the year 2000, let alone 2025, we're far out in the future. But at that time, the conventional wisdom was, by that time, we'd need a nuclear power plant on every street corner to keep up with the exponentially growing energy demand. And Amory just asked, well, what do we need all that energy for? And then after that, the corollary question he asked was, well, and couldn't we meet our needs for energy services with energy efficiency and more efficient technology at the end use rather than ever-growing energy supplies, whether it be fossil, nuclear, renewable, or what have you? And he projected a more modest trajectory of energy demand, more like the blue line here, at which point he was just absolutely overwhelmed with criticism and indeed ridicule by the energy establishment that couldn't possibly be true. The actual energy demand is actually the black line, to which now some people might say that Amory was right for the wrong reasons, but it's kind of hard to explain why these guys were all wrong for the right reasons. Nevertheless, it did change the discussion, it changed the paradigm, and really it just comes down to this. In the bad old days, we used to think about the energy system as the left side of this figure showing the energy supply chain. We start with the primary resource, oil or coal, or it could be uranium or a renewable resource. We convert it to an energy commodity like gasoline or electricity, and then we try to keep up with ever-growing demand for that commodity, then bearing the economic, environmental, security, and other externalities. And the paradigm change and the question that Amory asked was simply to say, well, that's not the whole energy chain. Once we have that commodity, we got to use it for something. And when we do that, we apply another set of technologies at the end use, and then finally we get something that we actually want. We don't necessarily want gallons of fuel or kilowatt hours of electricity, whatever that is. If you haven't taken the course, you probably don't even know, right? Instead, we want to move down the road or illuminate our task or heat and cool our house, whatever it may be. We want this service. In between those things, we have energy end-use technologies that provide the opportunity, by improving those, to provide the services we need with the same amount or even less of those commodities, and therefore their costs and their environmental impacts and security issues and reliability issues and so forth. And so the idea of meeting not just a demand for energy commodities, but what people actually want, namely energy services, cold beer and warm showers, unless you're English and you want it the other way around. But it's the service that we're after. And so that was the real paradigm change, to say what we're after is not exponentially growing commodities, it's what people need, the services as they evolve over time. And so here's, I think, what should be somewhat familiar, the so-called Sankey diagram, or we used to call it the spaghetti chart, of energy commodities and flows as they go through the economy from production to consumption. And it's ordered here so that the resource is on the left side, going through conversion and changing from, say, fuel to electricity, and some units are lost, and you come out here with the different end-use sectors. And then one more step in this chart actually shows the useful energy services derived, and they're gathered here. And then it shows this other really prominent energy service, waste. And that's actually the biggest end use still today. It's rejected energy, unused energy, wasted energy. And that's all simply to say that the potential, and therefore the available energy efficiency resource, is still quite large. Okay, so let's talk about how we use energy just real quick to set the background, because it's a necessary aspect of measuring and locating the energy efficiency resource. We got to be geeks, we got to be nerds here to figure out where energy is used, because that's where it can then be saved, and that's the efficiency resource. So we find ourselves diving into energy statistical information, and this is an example of the national energy accounting from the Energy Information Administration of the U.S. Department of Energy. Not sure if this will be available online, which is kind of an odd thing to say, but you might want to download the most recent editions just in case it somehow vaporizes, because it talks about information that's now verboten. Nevertheless, the basic methodology here is to say, how do we use energy? And if we look at the different sectors of the economy, you've probably seen this before, it's relatively equal between industrial energy use, transportation energy use, commercial, that is buildings where we work, and residential, that is buildings where we live. So buildings are actually quite prominent. And then if we drill down another level and look at a given sector and say, what are the end uses? What are the things that actually deliver those services that we're after? And what kind of energy do they use? So in residential, in our houses and apartments, we use energy for space heating and cooling, for heating domestic hot water, for cooking and sanitation and so forth, and then lots of other stuff. Lighting is a fairly small end use these days, and other appliances, and of course electronics and entertainment. And so we have to understand each of those pieces in order to imagine how to make them more efficient, if indeed there's potential to do so. So here's a little quiz. If we're talking about electricity specifically, which type of end use uses the most electricity all around the world? Is it lighting? That's the end use for which Edison invented the electricity system, essentially, in the 19th century. Is it heating? Is it electric motor drives? Is it electronic gizmos? Any idea, any strong feeling about that? Heat's the biggest user of energy, but most of that's actually not from electricity. A lot of it comes directly from fuels. It's actually the motor drives that's the largest user of electricity. And the reason for that is partly that the motor drives are embedded in a lot of the other things we think about, like cooling, for example. We use an electric motor to turn a compressor to run a vapor compression refrigeration cycle that makes cooling. If we have pumps and compressors and fans and all of those industrial equipment also use electricity. So that's why just the simple identification of the electric motor as a key piece of technology in all of those end uses is a really key piece of the energy efficiency puzzle. So let's talk about ways to save energy, assuming we've now got a decent understanding of how you use energy in the given sector or customer that you're working with. A lot of the potential for energy efficiency and that which is most accessible is in buildings. And you're going to get an excellent lecture about energy efficient buildings in a couple of weeks from Peter Rumsey. So anything that I say or misstate, he will fix and elaborate. But I'll give you just a quick kind of survey of what we think about when we talk about energy efficiency in buildings. We have to kind of distinguish a few subsets of the resource. The first thing we talk about is residential buildings where we live versus commercial buildings where we work. Okay, they're both buildings, but they have different they're different in terms of size, which changes the dynamics of energy flows, particularly for heating and cooling. Their occupancy is different. Residential buildings, we tend to be there all night. Commercial buildings, we tend to leave empty at night, but there's exceptions, things like hospitals and hotels. They have different types of equipment and so forth. So we have to really think carefully about how important a specific end use like lighting, for example, is in these different buildings. Another key distinction is thinking about existing buildings versus new buildings. New buildings can be designed from scratch. They can be regulated through building energy codes and standards. They can be addressed by different incentives. And you really have a lot of options at your disposal if you start early in the design process to make a new building efficient. However, most of the buildings that exist in, say, 2050 are already standing now, and they're not very energy efficient on average. And one of the great energy efficient resources is indeed the retrofitting of the existing buildings. But as you can imagine, that's a lot harder because the building's already there. There's a lot of things you can't change, or it's expensive if you do change them, or maybe it would be less expensive if you waited until there was going to be a renovation or a replacement of equipment, but then you have a time factor involved. So bottom line, retrofits are harder, but really important, and so we have to figure out ways to crack that nut too. Another piece of working on existing buildings is actually not necessarily changing the technology, but trying to assist the operators of the building to make sure they work, even as designed, even with the technology that's there. And it turns out if you go into most existing buildings, they don't actually work very well. And I've been in a lot of them and instrumented them and been a little bit horrified at how many controls, glitches, and inoperable components, and just bottom line energy wasting errors you find. And those things can be diagnosed and fixed apart from or together with retrofitting the equipment to make it more efficient, and it's an additional energy resource on top of the retrofitting resource that's often kind of overlooked, but is becoming ever more important. So having done all of that categorization, then we think about what are the end uses. So we look at heating, cooling, we look at lighting, we look at electronics and appliances and so forth, and trying to figure out the different strategies whereby we might improve efficiency. And in that, we kind of come across one other categorization, and that is all those things that are like equipment. You know, replacing the lights, replacing the refrigerator, power control on the computers, that sort of thing is equipment. It's hardware. Take out one piece, put in another, or in the case of the building commissioning, maybe tune it up so the thermostat works properly. And then there's the building shell, the fabric of the building, the skin of the building, which communicates thermally with the outside world. It lets sun in or not at certain times. Maybe the times when you want in the winter, maybe the times you don't want in the summer. It allows heat to flow in and out of the building due to the temperature differences between inside and outside. And again, maybe that's helpful, and maybe that's adding load on your HVAC system and causing energy use. And if you can mitigate those energy flows through insulation, for example, through better windows, you can reduce the load on the heating and cooling system, perhaps make it smaller and cheaper, but also run the building more efficiently. So we go through all of those end uses and try to figure out and design strategies to improve efficiency and use less energy while meeting or exceeding the need for energy services. So one energy end use that we almost don't think about very much anymore because we've made such dramatic progress is in electric lighting. We used to use incandescent lights where you might have a 100-watt lamp, and we in the 80s started replacing them with compact fluorescent lights, and they would use maybe 15, 20 watts. And now we have LED lamps that are even better in terms of their lighting quality, and they use less than 10 watts. And we were able to implement LED lamps much faster than we had the fluorescents back in the day because we had that experience with trying to implement the fluorescents, and we're able to use those policies and programs. But the LED lamp is really kind of an interesting story. LED stands for light emitting diode. So it's a little semiconductor device. And back in the day, I can remember one of the early energy efficient devices for things like cinemas and auditoriums. We have them here. Look in the back. You see the exit sign? So you'd be in a dark room and there'd be a little green exit sign, and it would be like a 25-watt incandescent light, just making heat and wasting energy. And you could replace those with a green LED and save most of the energy. That was kind of a cool thing, small but cost effective back in the day. We had green LEDs. We had red LEDs, but we didn't have blue LEDs. And without all three, you can't make white light. And it took a Nobel Prize winning breakthrough from a Japanese team to make the blue LED, hence the white LED, hence a revolution in efficient and highly controllable and tunable electric lighting. And so now we have cheap, efficient, very highly functional LED lamps. And lighting energy efficiency is now so easy that we almost don't think about it as a measure. But of course, we can still control the light, make sure we're not using it in unoccupied rooms and that sort of a thing, and thereby still improve efficiency and minimize our bills. So lighting's gotten pretty easy. Heating and cooling is still pretty hard. It's complicated. There's a lot of steps to addressing heating and cooling loads. The first step and the strategy they always recommend is start downstream and figure out how to reduce the load itself. What about that building shell? Can we add insulation, better windows, tighten the air leakage, those sorts of things? Can we reduce heat loads from equipment like lighting with more efficient lighting? All of those things reduce the load on the heating and cooling system. We can also control it more precisely and make the job easier for our equipment, the heating and cooling equipment, air conditioners, heat pumps, and so forth. Those can also be made more efficient. They can be controlled in a way to do things like using outdoor air when it's cool enough to cool the building rather than refrigerating air. Pretty straightforward strategy, but engineers have to have a complicated name for it, so they call it economizer. But not all buildings have been employing that, and so it's a control upgrade when you do. We can also capture heat from one end use, like the heat rejection from an air conditioning system, and put it into another place where we need heat, like water heating. Stanford does a nice job of that at the central energy system. And so we have a whole kind of portfolio of heating, ventilating, and cooling, HVAC or HVAC potential. And then again, controls, particularly in humid climates, where when you're providing ventilation for fresh air, you're also introducing a lot of humidity that makes the air, sticky and uncomfortable, and you need to remove that through the cooling system, adding energy use. You can control the ventilation in an energy efficient ways by using sensors and feedback. And again, the maintenance and the commissioning, that is the fixing stuff that isn't working as designed and as expected, is a complementary approach to efficiency in existing buildings alongside the efficient equipment. In residential buildings, one of the big locations of heat loss and therefore heating system demand is the windows. If you're familiar with electric circuits, you know that electric current is driven by voltage difference, and it's opposing a resistance. Well, it's the same with heat. So heat flow is driven by a temperature difference inside to out, and it's opposed by a resistance, a thermal resistance, which we measure with a unit, a strange looking unit, but we call it the R value, R for resistance, okay? And it turns out, conveniently, that one of the least thermally efficient surfaces we could put in a building, a single glazed window, has a R value of 1. So single glazing is R1. Double glazing, that's about R2. Triple is about R3. You can get R3 with a double glazed window that has a selective coating. We call it a low emissivity coating. And it keeps going. If you want to have 4 or 5 sheets, you could do that. But of course, at that point, it would get too heavy and expensive. But we've got other technologies. As I said, the selective thermal coatings can provide an insulating barrier to thermal radiation. You can fill the cavity between the multi-pane windows with an inert gas. That reduces the conduction and convection through those cavities. And you can get up to maybe R4 or 5 or 6, even R9 in an extreme case where you combine all of those strategies together. And that mostly eliminates the biggest heat loss source in a building. And so it can really have a big impact, particularly in new construction where you already have to buy windows for the whole building. Now, talking about retrofits in residential, again, retrofits are hard, but we're starting to see some innovation in thinking about retrofits not just as the piecemeal, well, maybe we can do some more windows or upgrade the heating equipment, but looking at the whole building. This is a program in the Netherlands called Energie Sprong, so Energy Leap, where they went in and surveyed these fairly old, very inefficient public multifamily housing units, and using laser measurements to get very, very exact dimensions of the building exterior, then produced factory-made exterior insulation panels with windows, brought them in, bolted them on to the house, added solar PV on the roof, heat pump inside, and in a couple of days performed a complete retrofit of the building that cut their energy demand by more than half in a very cost-effective way because of the mass production aspect of and the standardization aspect of the approach. And so, starting to think more big picture about how to overcome the difficulty of retrofitting buildings for energy efficiency, we're starting to see some useful examples. Now, talking about heating, and I'll get into cooling as well, but we should look at some of the common devices that are used. One of the things you see a lot of, some in California, you see a lot up in the Northwest, is electric resistance heating, a baseboard heating, where you're just running electric current through a resistor, and it turns that electric energy into heat energy. And you could say, well, what's the problem there? Whatever electricity goes in comes out as heat. It's 100% efficient. Can't beat 100%, can you? Well, actually, you can. In fact, 100% efficient electric heating, having paid to generate and transmit and distribute and use the electricity, is really inefficient. I'm calling it bad electric heat. And it's so bad, actually, that for a long time, the typical environmental recommendation is, well, replace the electric resistance heat with natural gas heat. That'll lower your emissions and improve your environmental footprint. And we've seen that, and we do see, regardless, in a lot of houses, particularly in California and the West, we see natural gas furnaces as the baseline heat. So you have a forced air system where we burn gas, warm up air in a heat exchanger, and distribute it through the house. And once we started to use condensing furnaces, we got efficiencies over 90%. Again, that's pretty good. It's hard to beat that with a combustion system. And you sure can't beat it with electric resistance or bad electric heat. However, even efficient gas heating still has significant carbon emissions. And as we get cleaner and cleaner electricity, we're rethinking the idea of fuel switching and going to electric heating to replace gas. But it has to be a lot more efficient to use that clean electricity in a way that actually reduces emission. But how can you get more efficient than 100% with a resistance heat? Well, we use a heat pump. And it turns out a heat pump can give you an efficiency more than 100%. If we said that, it would sound like bull. It would sound like some kind of fantasy thing. If you said, oh, well, my heating system's 300% efficient. So we don't call it efficiency. We call it a coefficient of performance. Now, doesn't that sound impressive? But that number is just a number like 3 that says we get 3 units of heat for every unit of electricity that we put into a heat pump. Yes, indeed, it's more than 100% more efficient, and I'll explain how that works in a sec. But this is kind of a game changer, because now we have the prospect of perhaps reducing those natural gas furnaces with their CO2 emissions with electricity from renewables and low or zero carbon at very high efficiency with a heat pump. So I'm going to call that good electric heat. And oh, by the way, we can also use it to replace all that bad electric heat, take out the resistance heat, put in heat pumps. You're still running on electricity, but now you're using maybe a third as much. So that's a really big win for the customer too. So this is kind of an exciting prospect. And I guess I will do my duty as a card-carrying mechanical engineer and take just a second to explain a little bit about how a heat pump, and therefore an air conditioner and a refrigerator, works. And if you're also a card-carrying mechanical engineer, maybe a grad student in ME, you might find this a little boring and repetitive. Feel free to correct my mistakes. But for everybody else, I'll just give a quick whirlwind tour of the world of thermodynamics. There's a couple of key laws. The first law is that you can't win. That is to say, energy isn't created or destroyed. It has to be balanced in any given system that's not creating nuclear reactions or anything. So that's a constraint, right? We can't just make energy out of nothing. The second law, and this is where it gets a little depressing, you can't even break even. So the second law, it's a little subtle, it's a little complex, and it actually gets into kind of a vague concept of the quality of energy. Energy that can do work, like mechanical work, or electricity, or the potential of lifting mass or water uphill is high quality energy. Heat is lower quality energy, but high temperature heat's pretty good. Low temperature heat is lower still. And so what the second law tells us is that if we have thermal energy, that is heat, it will move naturally from hot to cold. So if you're in your nice warm house and it's cold outside and you open the window, the heat will flow out. The air will mix, it'll get colder inside. It'll get incrementally, infinitesimally warmer outside because of that heat you just sent out. But heat will go that way all by itself. You don't have to help. And well, that's nice if you're cooling off a house and it's cool enough outside, you can do that. That was the economizer that I talked about in building control. But a lot of times it's cool outside and you want your heat to be warmer. Well, it turns out that despite those laws of thermodynamics, you can move heat from cold to hot. It won't go all by itself. It won't do that spontaneously. But if you add some energy, you can combine that energy with energy that you borrow from the cold outside and deliver it inside and get more than the amount of energy that you've put in delivered to the space. So you can get an efficiency of more than one. And that's what a heat pump does. So let me see if I can illustrate. Imagine if you took, let's say you have a big sliding door in your kitchen, and you take your refrigerator. And you take the refrigerator and you scooch it over and you put it in place of the sliding door. So instead of cooling the inside of the fridge and heating your kitchen, you're now facing the inside of the fridge into your space, and the back of the fridge is outdoors. Okay, now you're going to cool the space and reject heat to the outdoors. That's what an air conditioner does. Okay, your fridge is the same technology as an air conditioner. Okay, make sense? All right, let's flip it around now. Let's turn it the other way. And now let's cool the outdoors and reject heat into the space. Now you got a heat pump. So the heat pump is borrowing heat from the outside, just like the refrigerator takes heat out of your veggies, and then using some energy that you put into the compressor for the refrigeration cycle, then rejecting heat into the space, just as a refrigerator rejects heat into your kitchen. But it's not heat from the outside, it's heat from the inside of the box. And so the thermodynamics is the amount of heat that you get is the sum of the work that you put in and the heat that you borrow from the other space. Hence, more than 100% efficiency. Okay, so let's go into detail about how that works. It's this technology. It was invented by Willis Carrier back in the day when the only way we had to cool buildings was with ice, stored from the winter. But this you could do anywhere, anytime. And it relies on the properties of materials when they boil or when they condense, changing phase from liquid to gas and back and forth. So, for example, if I make tea here in Palo Alto, I boil water, and at what temperature does it boil? 100 C, 212 F, right? If I go home to Colorado and I boil water, how long do I have to wait for it to get to 100 C? Forever. It won't get to 100 C. It will boil at around 90 something. Why? Pressure, air pressure. The pressure is lower, and therefore the boiling point is lower. The vapor pressure of water, in this case, is lower. So the temperature at which a fluid boils, is a function of the pressure that it's under. And if you raise the pressure, you get a higher boiling point. If you lower the pressure, you get a lower boiling point. Well, if we take a gas that's tuned to boil and condense at just the right temperatures, we can have it boil where we want to collect heat, even if it's cool, like in the freezer of our refrigerator, where we're taking heat out of that freezer to keep it cold, right? Or the outdoor world when it's freezing cold. And then we can condense that fluid at a higher temperature where we want to deliver that heat, like the space that we're trying to heat. Okay, so let me illustrate how we do that. So let's start. We're gonna do a cycle. We're gonna go around the horn here with this thermal cycle. We're gonna start here with a cold, low pressure liquid. Okay, so we can't really do much with that to heat our house, but that liquid, because it's cold, but it's not so cold that it can't collect heat from the outdoors, okay? And it's at a low pressure, so it's going to boil at a low temperature, namely around that outdoor temperature. So this cold, low pressure fluid is going to collect heat from the outdoors, and then it's going to boil. And it's going to become a cold, but not quite so cold, low pressure vapor or gas. Okay, well, we still can't do anything with that. But now we got a gas. And so this is where we have to put the energy in. So now we run our compressor and we put some energy in. This is what costs us energy. We compress the gas, and then what do we get? We get a warmer, high pressure gas. Okay? Well, now that's interesting because we take that warm, high pressure gas and we bring it into the space, and now it's warm enough to heat the space. It transfers heat into our house. That's a good thing. And in so doing, that cools the fluid and it starts to condense. It goes back to a liquid. Still at high pressure though. Okay. Now we can't do much with that high pressure liquid, so we have to run it through an expansion valve, or in a big industrial system, we might even use a turbine to extract some energy. But we lower the pressure and we go back to our low pressure liquid and we go round and round and round. Each time through the cycle, we bring heat from the cold outdoors, or if we're a refrigerator, from the freezer box. Okay, we add some more energy to that heat with the compressor to get the high pressure gas that we need to deliver heat, and then we dump the heat into our space. Okay, and again, the efficiency is the sum of those inputs. The work from the compressor and the heat that we borrow, that becomes the heat that we deliver, and it's greater than the amount that we pay for in running the compressor. So the COP is more than 1. The efficiency is more than 100%. And if you think about what I said about thermodynamics being high temperature heat is higher quality than low temperature heat, it should make sense that as the temperature difference gets greater, as we're pushing higher up that temperature hill, that thermal hill, it gets harder and the efficiency goes down. The narrower the temperature range, the easier, that is, the more efficient, the higher our COP. And so if we want to think about, how could we make the system more efficient? Well, one way would be to lower the temperature that we're trying to deliver heat. Okay, well, we want to be comfortable, but there's ways we can do that. For example, if we have a well-insulated shell, then the radiant temperature and the temperature at which we feel comfortable will be the radiant temperature will be higher, and the temperature at which we feel comfortable from the air will be a little bit lower, so we can drop our indoor temperature and still have comfort and run our heat pump more efficiently. Or we could have radiant heating, like if you're heating the floor. Again, that makes you feel warmer even at a lower air temperature. So that's one strategy to reduce the temperature hill that your heat pump's climbing. Another way is to get your source temperature higher. Well, I mean, outdoor air is what it is, but what if we use the ground? And so another approach is to use, and I'll show a little detail on that in a second, is to use the ground as your heat source, which in the winter tends to be warmer than the air, and therefore you get a higher efficiency. Okay, so heat pumps they're not ubiquitous, but they're widely available. And so I was just describing using a heat pump for space heating, which is our biggest use of energy in residential buildings in most climates, the ones that need heating. Let's see, the picture here, this is actually the Energy Lab. It was built by Gil Masters back in the 80s, and we still use for CE 176A. Once you have this ability to use good electric heat to deliver heat from an electric source at a higher than 100% efficiency, we can do heat pump water heaters and make a much more efficient electric water heater that way, possibly reducing use of gas or replacing electric resistance heat. We even have heat pump clothes dryers now, again, providing a higher efficiency electric source for doing your laundry. And so those appliances are becoming more widely available, more cost-effective, et cetera. As I said, one way to make the heat pump even more efficient is to moderate the temperature difference that it has to overcome. And so the idea of a ground-coupled heat pump or ground source heat pump, some people call these geothermal heat pumps. So you'll hear that name. I hate that name. It's not got anything to do with geothermal energy. You're not extracting heat from, the volcanoes of Iceland here, right? We're just using the ground as a moderating temperature bank, so to say, or thermal bank. And so to collect heat or reject heat in the ground, you need a lot of surface area for your heat exchanger. And so you have to either drill down in a bore, or you have to have like a field of horizontal loops to exchange energy. And you can imagine that's pretty expensive stuff. And ground source heat pumps tend to be more expensive than other heating sources. But in certain applications, particularly in larger buildings, if the ground is relatively amenable and the water table is high, especially, they can actually be a pretty cost-effective way of heating and cooling buildings, because it's like always 55 degrees in the ground. And so if you're heating, you're only heating a little bit. If you're cooling, you're only cooling a little bit. And so you get fabulous efficiencies in a heat pump and air conditioner. A lot of those things I talked about so far are really promising ways to improve energy efficiency and save energy, and we call them measures. We look at an end use and we say, oh, how can we improve that end use? That's an energy efficiency measure, and we can say, how much does it save and how much does it cost? Is that a good deal? But it's not the kind of gold standard of improving energy efficiency in buildings. What we really want to do, and this is much easier with new design than in retrofits, but what we really want to do is to look at the whole system and use the interactions and the synergies within a system. And so when we think about tallying up all of these measures for energy efficiency, maybe reducing the heating and cooling load, we tend to think that as we do that as we try to save more, we're going to find higher and higher costs. And at some point we'll say, this is getting too expensive. Marginal cost is greater than marginal benefit, stop. But if we think about the whole system, what we can find, and what we often do find, is that there are synergies where, for example, once you've reduced the cooling load by a certain amount, you're done. You might not even need air conditioning. And so all of a sudden, all that capital cost goes away, and you can justify, a little bit more of your fancy windows or your fancy air sealing or heat recovery ventilation, whatever it is, and you can get more savings at the same or even a little bit less cost. And so we think about what Amory calls tunneling through the cost barrier by trying to use really ambitious energy efficiency improvements to downsize or even obviate the supply of heating, cooling, and other end uses. But to do that, you really have to look at the whole system. If it's a building, the whole building. The skin and the equipment and the weather and the ventilation and the occupants. And that's part of an approach that we call integrative design, which is kind of a combination of what the D School calls human-centered design, where we really focus on the service that we're providing, the energy service in this case, and then work upstream and try to figure out how to provide that with greater efficiency. And only when we've done all of those things, we start to think about the supply of energy. And it turns out, we need a whole lot less, and that makes the whole system cheaper. And we're combining that human-centered design with a kind of an ecological systems design. We look at the entire system in which we're operating, figure out ways to combine different systems, different components to create synergies and savings. And by the way, just as a commercial, Amory and I created a course on this. And actually, Diana and Holmes Hummel and some other people created the course back in, 2018? And I jumped on the bandwagon about 3 years ago, and Amory and I now teach this course. It's called CE 107R or 207R. We offer it in the winter and spring. And the title of the course is Extreme Energy Efficiency. So we do a deep dive on energy efficiency in all the sectors, including buildings, but also transport and industry and electricity. But the methodology of the class and most of the work in the class sessions is actually learning integrative design and solving real-world problems in teams in real time, on the fly, during our course sessions, applying integrative design to some kind of big, hairy, challenging problem that you've never heard before. And it's all good fun, and provides a lot of knowledge about energy efficiency, but also a thinking tool that's quite useful in this field and in other stuff throughout your education and hopefully your career. Next thing I want to talk about is what we call the barriers to energy efficiency. And there's a whole literature on this, and I'm going to gloss over it in a very cursory way, just to say that barriers to energy efficiency exist, or else we probably wouldn't even have to talk about this. And the fundamental barrier is really an economic one, that whenever we perform whatever design changes or equipment replacements to achieve energy efficiency, the benefits come over time. We'll get energy savings for 10, 15, 20, 30 years, which is great, but it's in the future. And if we have to pay for energy efficiency, and we typically have some incremental cost, even in a new design where we're replacing something we would have installed anyway, we often have an incremental cost. And we got to pay that now. And because we have to pay it now, that tends to discourage investment for a future savings. And then there's all kinds of kind of smaller incidental little corollaries to that basic problem, like the classic split incentives problem, where if you're a tenant, say you're renting an apartment or you're a business renting an office, you don't care about the owner's building. You're not going to pay to fix that up. Similarly, the owner doesn't care about your energy bill. He's not going to pay to save you money. And so nothing ever gets done, no matter how cost effective your LED lights and your heat pump and all your other fancy gizmos are. And so we can look at that problem and most of the problems in energy use and say, oh man, there's really cost effective ways to save energy with a 1 or a 2 or a 3 year payback. And in financial terms, that seems like a home run, but it doesn't get done because of these barriers. And again, I'll refer you to the literature where they show what kind of discount rate energy users appear to apply to efficiency investments, which seems kind of irrationally high. We can also think about lack of information and other financial barriers. But bottom line is there's a big gap between what we see in terms of sort of automatic investment in energy efficiency and the potential that we can identify to save energy and emissions and money in a very profitable way using efficient technology and design. And in the policy world, that gap has arisen when traditional policy was typically limited to, okay, we'll provide public information. Well, maybe we're not even providing that anymore, but generally it was thought you should provide the public with information and consumer advice. You should fund research and development and support the advancements of technologies. And if you really want to push the market, so to say, you might have fiscal measures like a tax or a subsidy. And that is to say, changing the price relationship between energy supply and energy efficiency. And those measures can work, but they tend to still be subject to all of the barriers that we already observe to energy efficiency. So raising the price, when someone won't accept a 3-year payback and bringing it down to a 2-year payback might not be sufficient. So instead, we've started to look at more targeted, complementary energy efficiency policies, and I'll highlight 2 categories of them. One is efficiency standards, which can include building codes, to basically say you can't produce a product or a service unless it meets at least a minimum level of efficiency, kind of getting rid of all the laggards in product performance or design. Another category I'll talk about briefly is where energy utilities provide efficiency programs on behalf of their customers in order to reduce their bills. There's other approaches, technology procurement via states or joint ventures with states and utilities to advance kind of the high efficiency end of the performance market. I'm not going to talk about that too much. But yeah, so let's start with codes and standards. Energy efficiency standards are by far the most effective and cost-effective way to save energy, where we've used standards, and they continue to provide promising potential for further efficiency gains. In its simplest form, an efficiency standard just says if you're going to sell a widget, it has to have an efficiency performance of X or greater, and if it's less than X, that's prohibited. And so it puts all producers on an even playing field. They know what that criterion is. There's a whole lot of variations to standards. They can be prescriptive, where you stipulate you have to use this kind of technology and it has to have this performance. Or you can be more flexible and talk about performance. Like in a building, for example, it's hard to make prescriptive standards for every piece of technology. And even if you do, then you get an overall performance level from complying with that list. And then you can say, okay, let's be more flexible. Let's say you have to meet that level of efficiency that you would have gotten from all the widgets that comply with the standard. And that level of performance will meet the standard. Or you can comply any other way by changing the design, maybe using more solar or some other design synergy. Any performance strategy that meets or exceeds the overall standard is acceptable. So there's different strategies to implementing efficiency, and their existence overcomes the lack of consumer information. They require the provider of energy-using hardware or the designer of a building to collect that information and to know enough to make the building sufficiently efficient to meet the standard. They also mitigate the risk of producers of delivering to the market a more efficient but perhaps slightly more expensive piece of hardware and not knowing if the consumer will be willing to pay for it by simply eliminating the opportunity to continue to produce the less efficient widget. Now, you can imagine that you can't just impose this kind of thing on the market. You have to study it. You have to look at where the existing product lines are, where the technology is developing, what's available, what you expect to be available, and what it costs. And indeed, that's exactly what the agencies and the government entities that develop standards do. The California Energy Commission, the Department of Energy, and so forth, have a bunch of us nerdy folks who figure out the cost-effective ways to save energy, such that when you say the efficiency standard for this type of appliance is X, we know that by meeting X, it will save so much energy and cost a modest enough amount extra that it's going to be beneficial to just about every consumer all the time. And with technology development, it will probably get better and easier over time. And that's pretty much what we see. And indeed, we can update and tighten the standards over time. So as an example, going back historically, again, starting back in the bad old days of the 70s, if we look at the simple fridge freezer in your kitchen, and we look at the blue line, that's the average size of a new refrigerator. And you can see it had kind of already filled up the kitchen by that time, but it's gotten a little bit bigger over time. The green line is the cost, and we can see that, corrected for inflation, fridges have gotten cheaper over time, so we certainly haven't broken the bank by making them more efficient. But the red line is the average energy use, and we've gone from about 2,000 kilowatt hours per year down to about 400, so more than a 75% reduction in refrigerator energy use on average. And each of the little steps corresponds to a tightening of first the California state appliance efficiency standard, and then later federal standards. And you see a little plateau in the 90s, which is kind of interesting. You know what happened there? CFCs, ozone hole, bans on refrigerants that deplete ozone because of their chemical, basically the chlorine. And in the decade where those were phased out and replaced by ozone-friendly chemicals, we kind of took a break with the efficiency standard and said, okay, focus on the refrigerants. And that was solved. And then we continued on our merry way with more energy efficiency. But I mean, what's the big deal? You're talking 2,000, 15, 1,600 kilowatt hours a year. That's kind of trivial in the grand scheme of things. Well, there's over 100 million fridges in the country. And you start multiplying those numbers together, and you're getting tens of gigawatts, you know that term, of electricity saved. That is to say, we didn't have to build, we didn't have to fund, we didn't have to site, we didn't have to endure or clean up the pollution because of fridges. And so actually this end-use savings stuff can be pretty material. And we see this not just with fridges, but with other, top graph is for TVs. Again, you see the efficiency going down, size going up, and lots of other appliances that have gradually achieved a greater level of energy efficiency. In the bottom case, we're talking about a voluntary standard called Energy Star, which was started by the Environmental Protection Agency back in the 90s, which is a way of combining some of that public information with aligning with the standards that exist for some but not all appliances. I guess that's another thing that's on the chopping block today, which simply indicates that it's a successful program for saving customers money and the environment. A little bit more on standards. So as I said, some standards are kind of prescriptive, like refrigerators, like, okay, 500 kilowatt hours. But with buildings, it's more complicated. So for building lighting standards, and again, this is getting really a lot easier because of LED technology, we're a little bit more complex. So the table here is from the California Title 24 Building Energy Efficiency Standards. And what we do is we recognize, well, different buildings and different spaces in buildings need different intensity and quantities of light. So we can't give them all the same standards. So we have a prescribed standard for each of those different kinds of spaces. It's higher for hospitals and lower for offices, for example. And it evolves over time as technology enables us to improve efficiency at lower cost and more easily. And so for each year, for each space, we see a lighting budget in watts of lighting hardware per square foot of floor area. And the idea is you can meet that any combination of technologies, design, daylighting, et cetera. And it's been gradually tightened over time, again, as the technology has evolved, but it's specifically tailored to the different types of spaces to make sure that it's reasonable to comply with and still meet the energy service that we're after. We can combine energy efficiency in buildings and their standards into building codes that say, if you're going to design and build a new building, it's got to achieve a certain level of energy efficiency. And we have, fortunately, the standards are not really something that are in federal jurisdiction. It's more a state level where the jurisdiction applies. And in some states, Colorado is one actually, even at the state level, you can't impose a building efficiency code on everybody. It actually has to be at the local level. So in Colorado, we have really strict standards in Boulder, not so much in Colorado Springs, and in between in Denver. So it's kind of interesting. But nationally, we have a couple of different templates for energy efficiency standards. We have the International Energy Conservation Code, IECC, and we have the Standard 90 of the ASHRAE, American Society for Heating, Refrigerating, and Air Conditioning Engineers, provide recommended templates for efficiency codes that states or even local jurisdictions can adopt. And they get updated every few years and tightened again as technology improves. And what you see is different states, depending on their level of ambition adopt either an older, less stringent code or a newer, more stringent code, depending on their preference and their politics. But in any case, we still create kind of a spectrum of gradually improving and tightening energy efficiency codes at the state level. And so you can imagine if we think about as a efficiency technology or design strategy is adopted, you kind of go through that process of adoption, and the old thing of, you get the early adopters, and then you get the chasm where you're not sure you can get to a bigger market share, and then you get to mainstream adoption, and then you get to trying to sweep up the laggards. And the efficiency standards aren't about innovation and new technology. They're about getting rid of the laggards, okay? If you're gonna say everybody's gotta comply with that, you have to be really a little conservative and careful to make sure that it's really cost effective and you're not putting anybody out. And so, yeah, it's over on that side of the scale. Similarly, R&D is kind of way over on the left-hand side. We're trying to introduce new emerging technologies and so forth. In between, there's a whole range of adoption where you just want to sweeten the deal and get greater or faster adoption and implementation. And one of the strategies for that that's used in a lot of states, including California, is encouraging and incentivizing energy utilities to procure efficiency to help their customers save energy in order to reduce their bills. And it's again, it's a little bit of a complicated process because we're trying to overcome these barriers to energy efficiency. And all utilities have, customer relations and customer outreach. They have information and educational programs. They can do energy audits, refer contractors, and so forth. And that's great and that's necessary. And as we saw before, that's not sufficient to drive a lot of energy efficiency investment. What we need is a little bit more, basically some money on the table. So we use financial incentives to encourage customer investment in efficiency. And the most common thing that utilities use is just cash rebates. And it turns out to be a pretty effective way of capturing a lot of commercial efficiency investment, a lot of residential, but mostly at the more affluent end where people have the cash to make that expenditure and then wait for the rebate check to arrive. And the challenge remains how to deal with people that don't have the cash up front. And so the obvious way of addressing that would be some kind of financing, figure out a way to pay over time, reduce the cash up front maybe to zero. And so there have been subsidized loan programs for energy efficiency over the years, and they've failed dismally. Nobody wants to borrow money to save energy. Nobody wants to expand their balance sheet or affect their credit report. It doesn't work. However, we figured a little workaround for that, and there's some new approaches we refer to as on-bill financing or pay-as-you-save, where you effectively lease the efficiency technology to the customer address. Okay, so the obligation stays with the meter, and so somebody moves, they don't take it with them. It stays with that address, and the idea is to create a situation, and it doesn't go on your balance sheet, it doesn't go on your credit report, and you create the situation where you have zero cash up front, that's the right number, and you have a lower monthly payment on account of the energy efficiency savings are greater than the financing cost, the lease that you pay on your bill. And so it's a effective way of financing utility procurement of energy efficiency. It's working in a number of areas, but in particular, it's had success in Midwestern rural electric co-ops working with their customers to implement efficiency in places, where you wouldn't see them on the map of, kind of the blue states where they're pushing efficiency on account of its environmental benefits. It's strictly an economic, let's save the customer money, keep the farm in business kind of application. So there's really been kind of an exciting advancement in efficiency implementation via utility financing, combining a concessional finance with a financial instrument, but figuring it out how to do it in a way that it doesn't stick to the customer if they move, and it doesn't stick on their credit report or balance sheet. And so that was kind of an exciting thing. So bottom line, there's a whole kind of portfolio of approaches that utilities can use to invest in energy efficiency, and that they need to be tailored to the specific customer type and specific technology. So going back to that discussion of the analytics and how we find the efficiency resource, and again, just to show that we really need to be nerds and geeks to do this, the roadmap for identifying and prioritizing investments in efficiency by utility, for example, is the efficiency potential study. And typically what we do there is we stratify different opportunities for efficiency investments. And we start by just brainstorming all the possible technologies that you could throw into a building or a factory or what have you. And we develop what we call the technical potential. And so if something doesn't really seem to work in a way that saves energy, it's not technically feasible, but everything else goes in technical potential, and it's a lot. And it's actually only limited by kind of information and imagination. And as such, yeah, it's not very useful. But then we sharpen the pencil and we say, okay, if you're going to implement that widget, how much is it going to cost? And we look at the incremental cost compared to the savings and say, is that ratio satisfactory? Does it meet the threshold to say it's a good deal for the customer? If it is, it qualifies as part of the economic potential for efficiency. If it costs too much, we throw it out. So now we have a subset of technical that we call economic. And then we get a little more hard-nosed and we say, okay, well, what about our programs and our marketing and our implementation strategies? How much of this can we achieve? And in particular, how much can we achieve in a certain time, in year 1, in year 5, in year 10? What is the rate of achievement of that economic potential that we can actually capture with real programs that we can deliver? And that's the achievable potential. And you have to be very realistic, very perhaps conservative, and hard-nosed in your analysis, because this is the potential where you're going to say, okay, we're going to do that, and we're not going to fund the fossil plant, okay? If you're going to replace the fossil plant with negawatts, you really have to believe these numbers. You really have to be careful that it's going to work. And an example of some folks that do that is up in the Northwest Power and Conservation Council that was set up under the 1980 Northwest Power Act has been producing an electric resource plan for the whole region, 3.5 states, going back now 40 odd years. And every few years, they produce a ranking of the electricity resources to provide new energy services. And they compare supply side and demand side, fossil and renewable. And lo and behold, year after year, decade after decade now, they're finding that the majority of the cost-effective new electricity resources are negawatts, energy efficiency and the savings. And they have some renewables and they have some gas. But over the years, that's how they've kept the lights on, to the point where the achieved savings from the 80s to say 2020 was on the order of 2 times the output of the Grand Coulee Dam in Washington. Now, the Grand Coulee Dam just happens to be the largest power plant in the country. So that's kind of an interesting basis of comparison. But what that means is that's all the megawatts they didn't deliver and didn't have to build and fund and site and endure the environmental consequences because of the negawatts that were achieved, and they still see that going forward. So one place where policy sort of meets up with this procurement approach is some states, and you, again, can look at the map and kind of see the usual suspects. They have a standard for the utilities to say, We want you utilities to invest on behalf of your customers enough to save a certain amount of additional megawatts per year. And different states have different levels of ambition in achieving those savings on behalf of their customers. Over the years, the champion has really been Vermont. They're kind of in second place on this fairly recent graph, but they've been capturing a good 2% a year of incremental savings through efficiency procurement for a good long time, because they just simply prioritize that. And they actually created their own standalone administrator. They call it an energy efficiency utility. That's all they do. And lo and behold, they do it pretty well. Going back to the idea of a utility running its portfolio and weighing investments and supply side and demand side, the efficiency investments are actually one component of a little bit broader strategy, what we now call, in a very ugly term, demand side management. So demand side management is thinking about how to tailor the energy demand in a way that is easiest, cheapest, cleanest, most reliable to meet with your supply resources. And that includes energy efficiency in a big way to bring down the total demand, but also things like demand response and shifting loads in time with energy storage or with control technologies, so that you mitigate energy peaks. Or today we don't talk about demand peaks, we talk about net load peaks. Demand net of the available renewables that make it easier to supply energy when they're available, but then leave a peak perhaps at a different time. Today, we're adding another element to demand side management, which is electrification. Okay, so we're looking at the vehicle and the ability to replace dirty gasoline with clean electrons. And that's a huge win in terms of energy efficiency and emissions, but it's an additional load. And so that's got to be balanced by supply or other savings. But that 80 kilowatt hour battery that you drive around and connect to your house, eventually we're going to be seeing that as a resource to the grid because of the flexibility of when we charge it. It doesn't have to be immediately on demand. So it's a kind of a new type of load that creates both energy demand but also energy flexibility, maybe even a storage element. So energy storage is part of demand side management. And as we electrify buildings, like replacing gas with good electric heat from heat pumps, that will add a certain amount of demand. But at the same time, if we use those heat pumps to replace bad electric heat in resistance, it'll mitigate demand. So there's a whole complicated portfolio, and that's why the utility space has become so dynamic and interesting. And it's really the crux of where decision making is being made, having to do with energy decarbonization, because it's about efficiency, it's about demand side management generally, electrification, renewables, et cetera. Sorry about the graph. Please don't squint at it. This is in the readings. But the International Energy Agency, the IEA, talks about efficiency being a policy package of regulation, like those standards I talked about, information, yeah, necessary but not sufficient, and incentives, like the procurement or the financing or tax credits and so forth, as being kind of a sweet spot for a portfolio of policy measures to capture the technology improvements that we see in energy efficiency. And so to really achieve decarbonization, we really think of those three pillars, two of which are the demand side. So first, ubiquitous improvement in energy efficiency in buildings, factories, vehicles, et cetera, to contain the overall footprint of the energy supply enterprise. Decarbonize electricity supply. No doubt you guys are talking a lot about how to do that and the progress that we're making with renewables and the interface with storage to balance the time variation of those sources. And then once we've got clean electricity, back to the demand side, electrification of vehicles, of replacing gas heat with good electric heat, et cetera, can further reduce the footprint of those. And so we talk about an end use like a building potentially being net zero energy. How do we achieve that? This is the Bullitt Center, a 5-story office building in Seattle that was for a while, and maybe still is the largest net zero commercial building in the country in sunny Seattle. What's up, California? But anyway, how do you achieve that? Well, you put a bunch of solar on the roof, right? But in a big building, that's kind of limited. How do you make it net zero? Well, you reduce the energy demand to the point where the energy production equals it, and you got yourself net zero. So the strategy of net zero, whether it's a house or a whole community, or an office building in this case, is make the load so efficient that the supply can meet it. Just from my former neighborhood in Bellingham, some very modest income housing made very efficient nonetheless in cost-effective ways and ready for solar to make it net zero. Even modular homes, this is in the efficiency champion Vermont. Again, modest income housing made net zero and so forth. So bottom line, sorry about all the text on the graph, but whether you're talking about a country or a community or a building, you could say, well, I could be zero emissions. All I need is enough renewables, right? And zero emissions, I'm done. Fine, that's nice, but think about the building, think about the community. It doesn't matter. You're going to need so much of that supply that you're going to have limitations on the area, on the environmental impact of even the renewables, which isn't zero, of the cost, et cetera. And so the way to contain that footprint is through efficiency. The way to achieve decarbonization faster, you can build renewables at a certain rate, but efficiency is just as fast, and the two are complementary and will get you more total savings per year. And of course, the cost effectiveness is the key advantage of efficiency as a resource in pretty much all sectors. I'll say one other quick little thing. What if you don't do any of this? Well, you get Texas, okay? Now, back in 21, February 21, you probably remember there was this big winter storm, unprecedented in Texas, and they had all kinds of problems, but in particular, they had electric blackouts, and it was deadly. People froze. People lost power and water and everything else. And, at first the governor blamed wind farms, which was kind of weird because the wind farms were actually one of the few resources that was working. But then everybody else, observed that some of the nuclear plants shut down, a lot of the gas plants shut down, either because they didn't work or because they had sold so-called firm power that is guaranteed, like you have a seat on the plane, but they had bought fuel in the form of natural gas, non-firm, that is, they're flying standby. And guess what? When it got super cold, the gas utilities bought up all the gas and they didn't have supply. They couldn't generate even if they wanted to when the machines worked. But they had something like an 18-20 gigawatt shortfall of supply. And ever since then, Texas has been scrambling to figure out how to avoid that from happening, which is good. But what they're totally ignoring is that they had over a 30 gigawatt spike in demand. They didn't see 30 gigawatts because they couldn't meet it, and so they had blackouts before it was measured. But it was a result of having millions of crappy, inefficient, uninsulated, leaky buildings heated by good old bad electric heat. And so the demand spike in that cold snap was so great they couldn't possibly keep up with it. And had they followed California and, well, don't say California, any other set of more proactive states with efficiency standards, with utility procurement, with efficient housing, with heat pumps and good electric heat, a lot of that could have been avoided and it might not even have been an issue. And so just to say that this efficiency stuff, yeah, it's about the environment and it's about saving customers money, but it can even be a life and death benefit in cases where it really improves the robustness, reliability, and resilience of the system, because bringing down demand does all those things just as well as increasing supply, and probably a little more reliable. So that's the gospel according to Amory and I. And if you're around next winter and spring, we'll probably have our course available if you're interested in that too. And thanks to Diana and the team.